Hey, it is noontime, and a warm welcome to our today's Maritime Innovation Updates. And my name is Johan Bergman. I will be moderating this session. Today we have a speaker, Mr. Rachid Srivastav. Rachid holds a master degree in operations and management in maritime systems. Rachid works since 3 years at Fraunhofer CML at the group Port Technologies, and among others, he deals with port operations and discrete event simulation. And actually, this presentation by Rachid bases on a case study which we have conducted together with the company Kalp GmbH. And thank you, Rainer. I saw that you have joined this session as well. Thank you for collaboration in this area. During the presentation, please mute yourself and remain muted since the session is being recorded. Please leave your cameras off. And in case of any questions, please put these questions in the chat, or we can start the discussion after the presentation. Rachid, please start. The stage is yours.
Okay. Thank you, Johan, for such a nice introduction. And hello, everyone. So I would like to now begin the lecture on Quay crane simulation and identification model. So these are the topics what we are going to cover in today's presentation. And the next slide is introduction. So what is Quay crane simulation and identification model? Basically, it's a discrete event simulation model where we are comparing the single trolley and double trolley ship-to-shore cranes performances, and we are evaluating the performances based on a hypothetical vessel storage plan. In general, just to tell the viewers that single trolley ship-to-shore crane and double trolley ship-to-shore cranes are basically cranes which are responsible for loading and unloading the containers from the land side to the vessel. And as its name says, single trolley is where only one trolley is responsible for performing the task. And in double trolley cranes, two trolleys collaboratively work with each other to perform the same task. Now, going to the next slide, the concept for the simulation idea is that in central, we have a discrete event simulation model that we have developed, and that facilitates the user with three basic features. That is, it allows the user to have a configurable crane models. That means the user can choose which type of crane he wants to study and what dimensions and dynamic parameters he wants to put for the crane into the model. Second, we also provided the model with some additional features where the user can choose those additional features and can run different scenarios and could experiment with different scenarios with the model. And the results are developed in a form of bars and graphs so that it is very helpful for the user to understand the performances of both the type of cranes and during their operations. In the next slide, we can see the approach. So the model actually has three building blocks which work together to develop the simulation results. And as the name suggests, the first building block is configurable vessel bay size. That means that the user is allowed to model the vessel size. That means he can choose the number of tiers and the number of rows. And since the model is having a source which is generating containers, so the attributes of these containers are like tier number, row number, bay number. And then there are two types of discharging logic, that is logic 1 and logic 2, which I would like to explain in the next slide. And on the right side, you can see that there's a configurable handover times, which means the user is allowed to choose the type of horizontal transport he wants to cooperate or to couple with the to-shore crane to evaluate the performance of the crane. So these are automated guided vehicles and straddle guided. And in the center, we have like process time calculation where the trajectory motion of the ship-to-shore cranes, trolley movements, as well as the automated and manual lashing operations, these all are calculated and then final results are developed at the end of the experiment. Now, as I said, that there are two different discharging logics. So in this case, we actually considered the Lashkov operations on the vessel as well. So in short, Lashkov operations are those where usually for the top three tiers where the twist locks are removed with the help of Lashkov, then the containers are removed from tier by tier. And for our study, we have considered the discharging logic 2, where you can see here that the first right top corner, after the three tiers are removed, the right top corner, which is near to the quay wall, is removed, and then it goes in a triangular fashion. And then there are evaluation criteria, or we can say as key performance indicators. So we wanted to make the study very simple and very understandable to understand the behavior of the cranes. So we took only through two KPIs, that is crane cycle time. And in this crane cycle time, we are calculating the lifting time of the container, the trolley travel time, the lowering time, and the empty travel of the trolley back for the next container. So this is contributing to the crane cycle time. And then the average container throughput, that is how many boxes are being discharged over an hour. Coming to the next slide, basically an important slide which regards with the assumptions and the initial experiment conditions what we have took during the experimentation. So assumptions are that every container being discharged by the crane, whichever crane, that is single trolley or double trolley, it always happens in the back reach. And then the crane dynamics, which are basically average dimensions, and the trolley speeds, which we have referred it from some of the literatures from the crane manufacturers. So we didn't focus on specific model, but we tried to cover the average dimensions and the trolley speeds. Then there's a point that we don't want any delay of arrival of the horizontal transport, because we wanted to understand the behavior of the cranes. So we kept the arrival of the horizontal transport with no delay. Then the time periods like spreader locking, unlocking, and error times, these are not considered within the separately considered within the project within the study. And then there are numerical parameters like manual lashing time, which is around 40 to 50 seconds per container, automated lashing time 5 to 7 seconds per container, which is again referred from CALP, which is our study partner. And then straddle carrier handover times, which is around 30 to 40 seconds per container, and AGV handover times, which is 10 to 15 seconds per container. And this is in the case of coupled operations. And on the right side, you can see the snapshot from the user interface of the program, where we have put different parameters. Now, based on these initial conditions and experimental conditions, we were able to develop more than 15 or 16 scenarios. We were able to test 15 to 16 scenarios with the model. But for the sake of simplicity for today's presentation, we considered only 4 major scenarios, and that too with automated lashing operations. So you can see that in single trolley STS crane with straddle carriers, we expected we see productivity of around 55 to 56 containers over an hour. And when we work with AGVs, that is in coupled operations, we were seeing the results around 45 to 46 containers. And when we talk about double trolley cranes with automated lashing operations, for both the case, for straddle carrier and AGVs, we found similar results, that is around 35 to 36, 37 containers on an average. Now, based on these results and observations, we developed 2 major conclusions. First is that in case of double trolley ship to shore cranes, the slower speed of the automated second trolley basically limits the capacity of the main trolley. And that's why the main trolley waits for the second trolley to lift the container. In general terms, it can be seen that in the right side of the picture, the lashing operation platform is on the land side. And there you can see there's a productivity loss in the initial cases of, let's say, 30 to 33 containers. And that is basically because every time the main trolley lifts the container which is near to the quay wall and is waiting for the secondary trolley. Because in automated double trolley cranes, usually the secondary trolley works with slower speed as the main trolley. And then on the left hand side, you can see there are 4 graphs, and we tried to run the scenario with different trolley speeds. So there may be some hairstylists or crane manufacturers who have their trolleys running at 50%, maybe 60%, or maybe 70%. But we tried to develop the results for that situations. And we found that if the secondary trolley is working with 50% speed of the main trolley, there's much more of productivity loss. When it goes with 66%, it's around 30 around for 30 containers, the productivity is lost. And in very hypothetical condition, whereas the secondary trolley is 80% of the main trolley speed, and in case of 100%, there were no productivity loss. The second conclusion we developed is for the lashing operation. It was clearly seen that with single trolley ship to show cranes with straddle carrier along with AGVs. Here the result for the straddle carrier is that with single trolley the expected the viewed results were around 57, 58 containers throughput per hour. And then for manual lashing operation, it was around 38, 37 containers per hour, which is an ideal case. And then with double trolley, we saw the similar behavior of the crane, that the double trolley ship to shore crane showed a productivity of 35, 36 containers, and the manual one with manual lashing operation, it showed around 18, 19 containers. And below you can see the time factors, what we have considered for manual lashing operation and automated lashing operation. Now, what we are planning? So the next stage, we want to test the model with some real data sets from the terminal. And also in the future, we want to implement some distribution patterns as well as the downtimes of the machine, which is not considered in the present stage. So as I said, it is an ideal case. And then we also want to look into the crane performances, that is not just in the discharging, but also in loading and double cycle operations. And also we want to implement the acceleration, deceleration of the factors of the trolleys. There are many more factors with what we are looking forward to implement in the model. And I would say that this would be synthesized or tailored based on the requirement of the industry. So, sorry, that was the last slide. And these are the contact details. As explained by Johan, that the project idea was collaborated and worked together with Mr. Rainer Kapelski from Kalb GmbH. So these are his and my details, and we would be very happy to answer some questions personally and as well as after this presentation. Thank you.
Thank you very much, Rachid, for the presentation. And yeah, I would like to open the question session. And maybe I will ask the first question. Rachid, I saw that the amount of containers in the graphs was limited to 200. So I assume it was one bay. Did you consider to extend the model? So is actually the model extendable? Can you serve with the model the whole vessel? And if yes, I assume yes. What results would you expect? So is there any difference in the performance in the results?
Okay. So currently we studied like 23 rows of a vessel and 9 tiers of the containers, and with single bay. But the model is designed in a way that it could be extended for the whole vessel, and the results could be obtained differently when we are implementing more parameters like downtime of the machines, downtime of the trolley, and if there is some possibility, some situations where these twist locks are not getting opened or being stuck with the container, these situations we would be adding it in the near future, and then definitely the results will be different, but it will be more realistic, and the crane behaviors would be studied more better in that way.
Yes, I understand. So the detail level of the model could be increased. Indeed.
Yes.
And that actually leads me to another question. That's in conclusion number 1, you were mentioning that on the lashing platform was located on the land side, and at the same time you told that there were 16 or 17 scenarios which were modeled. Did you actually consider to play with the model and to put the lashing platform, we speak about double trolley cranes, obviously, on the other side, on the water side?
Yes. We were actually able to literally play with the model. We were playing like 16, 17 scenarios, different scenarios. And we also tried to model this scenario where the lashing platform for the secondary for double trolley crane is on the water side. And we found very drastic results, because in that case, the productivity was much more reduced. Because from physics point of view, you can see that the secondary trolley, which is already working with, let's say, 66% or 50% of the main trolley speed, it takes more time to travel. And this traveling distance increase has somehow resulted in lower productivity. And it was seen in the result that most of the time the main trolley was waiting for the secondary trolley, even though the platforms, that is the positions for lashing operation, that was already filled, but still the crane was waiting. Yeah.
Okay, I understand. Thank you. Any other questions from the audience, comments on the presentation? this is not the case, then we look forward to next steps in simulations in this project. And yeah, thank you very much for having joined us. Please come next Friday to an interesting presentation of my valued colleague Cosmin Delia, and he will be presenting the results of hunters and gatherers maritime litter datasets. Then have a great afternoon, have a good weekend, and I hope to see you soon. Bye-bye.